Okay, so for this video, I'm going to be going through page 649, number 13, D and E. This is coming out from 12.4. For page 658, I'm doing number 23, 29, C and D, and number 33, A and B from 12.5, which is what you guys worked on today. For today's video, and pretty much for the rest of the videos of this week, I will gladly take any request of problems you guys would like to see up on a video. So go through all the problems that we've done and send me an email or just shoot me some type of request. Maybe tell me in class on Wednesday. Tell me some problems you guys want to see, and then you'll get your problem up on the YouTube, and I will talk you through it and walk you through it, just in case we don't get to it in class. So since I won't be here tomorrow, make sure you email me some problems either tonight or tomorrow, so that I can make the video and get them up onto the YouTube, so that you guys see them when you want to see them. Okay. So there will be a video tomorrow night too. Just know that, and make sure you guys just get your input in. It's no fun if it's just me talking at you guys the whole time. As for these problems, I really recommend taking a look at 29 and 33. The other ones, if you feel you have a hang of it, you guys can feel free to skip it, or just enjoy the show and watch all of it. So let me get started. A and B, we're dealing with 6-letter permutations from the letters of Nimble. Okay, so on C and D here, for C, it says it wants the second letter to be a consonant and the last letter to be E. So 1, 2, 3, 4, 5, 6. The last letter, we want it to be E, and the second letter needs to be a consonant. Okay. Here's the deal here is that we have to think about which constraint here, if they play into each other at all. So is E a consonant? No, E is a vowel. So the second letter being a consonant isn't really going to affect that the last letter is going to be E. So we go through and we say how many E's are in Nimble. Well, there's only one. So there's only one way that we can have an E as the last letter. How many consonants are in Nimble? Well, there's 1, 2, 3, 4 consonants in Nimble. Doesn't matter which one it is. No, it doesn't. So there's 4 choices for the consonant. How many choices do we have left? Well, we've used 2 out of the 6 digits. So we have 4 choices left for this spot, followed by 3 choices left for this spot, followed by 2 choices left for this spot, followed by 1 choice left for this spot. We'll now just multiply straight across to give us our answer. Okay. In the second one, we have second letter is a consonant and the last letter is an L. 1, 2, 3, 4, 5, 6. So we have to be careful here. Okay. So because L is a consonant. Okay, so what we have to think about is what is the more pressing matter here? Which one is more direct? Which one is more, and are they playing into each other? And well, yeah, L is a consonant, so L needs to be taken care of first. So there's only one L in Nimble, so we'll just put 1 here, okay? But now we come to the consonant in the second spot. We want to say 4, and on the test, a lot of people made the mistake of saying, well, how many consonants actually are there? Well, we've used one of the consonants, so the only choice we actually have here is 3. And now we can say, how many choices do we have left for the first spot? Well, there's still 4 choices. How many choices are left for the third spot? There's 3, 2, and 1. We'll multiply this all together, and this will give us our number of choices for both of these. I'll leave this to you guys with the calculators. Okay, this is number 23 from page 659. It's dealing with a restaurant that has 6 different ingredients that you can have for breakfast. And then it asks for how many combinations can you have for a 3-ingredient meal, a 4-ingredient meal, a 3 or a 4-ingredient meal, which this is the interesting question here. And then a 6-ingredient meal. Well, let's actually start from the bottom here. How many ways or how many different combinations can you have of a 6-ingredient meal using all 6 ingredients? Well, this becomes a 6 choose 6. And there's only one way to have a plate full of all 6 ingredients. So there's 1. This is a lesson that if you have the number is 6 is your sample space, and how much you choose is the same number, so 6, choose 6. There's one way to choose all 6 ingredients, okay? So up here, this is simply just 6, choose 3. We have 6 ingredients to choose from. How many do we choose? 3. So 6, choose 3. Then 4 is 6, choose 4 for B. Okay. And then 3 here, it says 3 or 4 ingredients. And this or here, the or is the big indicator of what we're going to do. What we're going to need to do is we're going to need to add, since it says or. If it said and, we would multiply. But since it says or, we're going to add. So what we're going to do is we're going to say, how many ways can I have a 3-ingredient meal? This is just 6, choose 3. And then we're going to add this to the number of ways that we can have a 4-ingredient meal. So 6, choose 4. And then, of course, this is going to be some number, some number, some number. And again, I'll let you guys do this on your guys' calculators. So or is add. So we're going to take all the ways we can have 3-ingredient meals and add them to all the ways we can have a 4-ingredient meal. Okay, problem number 29 from page 660. This deals with a set of 10 students where there are 6 boys and 4 girls. And we need to find the probability that part C asks for 3 boys and 2 girls, or 3 boys and 2 girls. So the or here, okay, this means plus. And then these ands here, these mean multiply. Multiply, okay? So it looks like we have this probability here that we're going to multiply the probability of 3 boys and 2 girls plus the probability of 2 boys times the probability of 3 girls. Okay, so let's set this up. The probability of getting 3 boys, or choosing 3 boys. So how many boys are there to choose from? There's 6. So 6, choose 3. Okay, multiplied by our 2 girls. Okay, so we have 4 girls, and we're going to choose 2 of them. Okay, and we're going to add this to the idea of, well, how many boys do we want? We're going to do 6, choose 2, times 4, choose 3. So since it's a probability, though, okay, this is only give us our numerator. We need to divide this by the entire sample space, which is going to be 10 students we're choosing from. Choose how many on this committee? Oh, we were doing 5. Select 5. Excuse me, that was important. So we're doing 10, choose 5. Okay, again, this is going to be some number. I'll leave that to you guys at home with the calculators. Okay, part D asks, what's the probability that eloquence, okay, and eloquence is one of the females, okay, or one of the girls. What is the probability that she is going to be on, or in this group, okay? So we need to think, how many eloquences are there? Well, this is a pretty rare name. So I'm going to say, well, there's 1 eloquence, okay? And how can we choose her? Well, we'll do 1, choose 1. Okay, but we have to select, we're still selecting 5 people. Okay, we're still selecting 5 people. So how are we going to select those other 5 people? And how many people are there still left to select from? Well, there's still 9 people we can choose from. And how many of them are we going to choose? We're going to choose 4. We'll divide this by our sample space, which was 10 overall people. Choose 5. Okay. One way to check to see if you're setting things up correctly. Everything on the right side of the C's in the numerator, so see this 1 and the 4. Everything on the right side of the C should add up to the bottom number here that's on the right side of the C. So notice that 4 plus 1 equals 5. The same trick is going to happen on the left side of the C. So 1 plus 9 will always be 10, okay? When we only have one number up on top, when it's not an or, okay, when we only have one thing up on top, this will all add up accordingly. So everything on the right will add up to the right. Everything on the left will add up to the left. Okay, this is number 33, and I'm only going to do part A and B. What it says is that there are 7 cards. 2 of them are selected as winners. What they are, we don't care. We just know that there are 2 winners inside of this 7-card deck. And we're going to select 3 cards at a time. Part A asks, what is the probability of getting exactly 1 winner? And exactly is the key word here, and this means we can just do what we've been doing, okay? So, how many winners are there? There are 2 winners, okay? And we want to choose exactly one of them, okay? However, we still have to select a total of 3 cards. So how many more cards are there left to choose from? Well, let's see. There are 5 loser cards, and we're going to choose 2 of them. This will give us a hand of 3. Notice 1, 2, 3. Okay, so we're still selecting 3 out of the entire 7. So our entire sample space is going to be 7, choose 3. This will show us the probability of getting exactly 1 winner. Okay, the trickier part comes in part B. Okay, part B asks, what is the probability of at least 1 winner? Okay, and this would actually take a lot of computing that we'd have to do. Okay, we would have to take the probability of, because since it's at least, okay, if we think of a 3-card draw or a 3-card experiment, okay, if we had a winner, loser, loser, this is at least 1, okay? So this would be the probability of 1 winner. Okay? Then we'd also have another situation in which we could have 2 winners and a loser. So this is the probability of 2 winners. Okay? And the thing is that even 2 winners is at least 1 winner. Okay? Let's say that there was more winners in this deck. You could have if there's more winners, right, you could have 3 winners in a row, okay? And then you'd have to compute the probability of 3 winners, and you'd have to add all of these up, okay? It's just easier if we think of it this way, which is the probability of at least 1 winner is going to be equal to 1 minus the probability of no winners. Okay, so at any time that you see at least as a word inside of the probability, we want to rewrite the problem as 1 minus it never happening. Okay, so the probability of at least 1 winner is equal to 1 minus the probability of no winners. So how we'll compute the probability of no winners? Well, let's see. How many winning cards are there? There are 2. And if we want the probability of none of them being chosen, we're going to say 2 choose 0, okay, times how many of the losing cards do we want selected? Well, there's 5 of them, and we want to choose 3 of them. We still need to divide this by the entire sample space, which is still going to be 7 choose 3, okay? And then this will give us the probability of no winners. But we're not quite done. We need to compute this and then subtract it from 1. Okay, and this will give us the probability of at least 1 winner. So the big key here that you need to know is that if you see at least written in there, you need to do 1 minus the probability of the event not happening. Okay, that is my hint to you guys. If there's any questions or comments, please let me know. I look forward to seeing you guys on Wednesday.